Sure why this thing is showing up in the bottom of the screen, but there it goes. Okay. So for this last session, I figured I'd go through the rest of that overview presentation, which covers a bit more on, first one's a bit about where you can find more information. And then we'll talk a bit about source code, a lot of these keywords that Emmanuel mentioned, or you can find them in the documentation. You can also search them in the source code. So I'll give you a little, the source code is huge, but it's actually fairly organized. And so I'll try to clarify what that looks like. And then we can, next section is kind of summarizing, things that have been happening recently, what we're currently working on now, so you kind of see what's coming down the pipeline. And then, wrap up with little, future directions where we think we need to go. And then I think the rest of the session, that'll probably take 45 minutes or so. The rest of the 45 minutes we can use for whatever you guys want, either questions, help with some of the examples that Emmanuel went through. We'll play it by ear. Does that sound good? Okay. I know it's the end of a long conference, a long day. So, but please, make it interesting. Stop and interrupt and ask questions. So, okay. First about community, I think Emmanuel mentioned the GitHub site. This is the address here. You can find it, github.com/openfast, excuse me. And everything tied to OpenFAST, FastFarm, and all these most of the pre and post processes are here. So you can find the source code. You can find all the build systems, so you don't have to figure out how to build it yourself. We have lots of options for you. Most common on Mac or Linux, or even Cygwin. Generally recommend using CMake, and all the CMake scripts are there. So we have people here that can help you if you have issues with those things. On Windows, we generally recommend just using Visual Studio. You can download Visual Studio for free. The Intel Fortran license is free these days, the Community Edition, and so these are all free things. You can install them and press build, and it will compile for you. We do tagged releases, and actually the last one was a week and a half ago that Andy did back in the room there. With every tagged release, we have both a tag of the source code and all the regression tests. And then for Windows users, we provide these executables like Emmanuel just gave you for these tests. For Mac and Linux people, Homebrew sounds like the best approach, or you can do the compile through CMake. And then in terms of help and issues, like if you get stuck, there's a few things to do. We have on GitHub, we have the issues tab of GitHub is where you post, like, I ran this, it doesn't make sense to me, I think it's a bug. That's where you post a question. If it's more like, I don't know what I'm doing, I need to sort of more like a usage type question, we have a discussions part of GitHub that has that. If you want a new feature request, there's that option in the issues as well to say, I see this, but I really want to do that. You can put your request in there, and not guaranteed it's going to happen right away. That's where you do that. One thing about this open source nature of the code is that you can basically track all our development through GitHub as well. You can see all various forks. If you want to use Derek Slaughter's newest tight coupling branch, I'm sure you can find that. It's all on GitHub. And so it's all there. All our dirty laundry is basically visible for the community to look through, and you can select in open, in the repository, do you want the main one, which is our stable branch, or do you want to go to subdev branch somewhere to see what's been currently worked on. This repository also has a lot of the related software, like the Python toolboxes Emmanuel mentioned, the MATLAB toolboxes and so on are also on here. Terpson's on here. Let's see. The last point I had there was community contribution. I think I mentioned this at the very beginning. Like, we definitely encourage, obviously, if you're just starting out, you're just trying to figure out what to do and make use of the software. As you get better, eventually you're going to say, I want it to do this, and it doesn't do it, and you make a change to the code, you think it's an improvement, we have the options in here to basically submit that pull request to the community. So we really are encouraging community contribution, and the team over there, like Andy and Derek, are people that review improvements and make that happen for the community. So, and there's been some really good ones too. Like I think the LiDAR module recently that got put in was done by a PhD student in Strathclyde, is that right? And the original structural controller module was also done by a PhD student and so on. So there's some big things, obviously some small improvements as well, but we encourage all community contribution. And again, like I said, the process is laid out here on the documentation through this website. I think the process is clear. I think it always is useful if you plan to do a big change, just reach out to one of us, let us know what you intend to do. It's helpful to sort of talk through it. It doesn't take long to kind of figure out what you want to do, and we can probably nudge you in the right direction so you don't waste everyone's time by doing something that's not right. So again, that's more the gray area right now, but the process in terms of how the mechanics of it, I guess, are very clear on the code on the website. Documentation, obviously, there's lots of documentation out there. This is the website link there. It's called it's all in Read the Docs. There's a lot of documentation here. User guides, modeling guidance, theory. Is it 100% complete? Unfortunately not. But we do have lots of old things as well. Emmanuel mentioned like coordinate systems is actually really well documented in our FAST 7 guide. And so you can find those links through this documentation page as well. At some point, obviously, we want to make it fully, consistent and up to date. That's our dream. It's hard to get funding to make that happen. But that's certainly our goal. Obviously, this is another area we encourage community contributions. Like if you struggle through something, you finally figured out, like if I would have read this, it would have helped, please submit a request and we'll get it in there and make it better. So again, we're trying to make this a community thing, so to help everyone out better. Legacy, we do have this forum. I remember hearing a comment like, it's kind of old school these days. Actually, about a year and a half ago, there was an upgrade to a new discourse-based system. And when we did that, all the old data, so I think the original forum started in 2005. And so we're almost 20 years basically of people posting questions on this software. And so likely if you have a question, I guess I always suggest searching first, because maybe it's hard to figure out what to search for, but like there's 20 years of Q&A on the forum as well as on more recently on OpenFAST, and search first. Likely you'll find the answer because likely your question's been asked before. But if not, that's when you start posting a question. But you can still create an account here on the old forum. Again, it's still active. I think the participation's going down as GitHub's sort of ramping up. But a lot of the old legacy stuff is certainly discussed here on the forum. And well, if it turns out to be like people start talking about bugs that are showing up, we basically always force them back to the GitHub organizations. We track all bugs there. But usage type questions, really, you can find a lot of stuff here on the forum. So some of the tools that have been mentioned where there's no active development at all, they're just kind of sitting there. Stationary codes like B modes that we use for mode shapes are on this site here. This is where we kind of store legacy codes. You can also find like old versions of FAST 7 and so on if for some reason you need to go back to that, all on this page here. And so, we don't really update this site often. It's really meant for legacy things, all the active developments in GitHub these days. But some of the old stuff we reference, it's useful to find them at this page. I think maybe if you were here at the very first session with Raphael talking about the overall portfolio of software, I would say since we switched to GitHub 10 years ago, it's been harder to track usage. We used to do that a lot better when people made accounts on our site. So I don't have great numbers these days, but yeah, last time we were tracking usage, we had, it's about 10 years ago now. I guess we knew about 4,000 users of OpenFAST. I think nowadays it's much, much bigger than that. We just don't have a great way of tracking it. These are some of the again 10-year-old plot maps, though obviously a lot of US, a lot of Europe and Asia and so on. But yeah, I think Raphael's also trying to work on better ways of getting more recent data on all the tools. But in terms of usage, I would say if you look at sort of the pie chart, I don't have it on here, but the pie chart, I would say half the users are probably academia, PhD students, people doing their thesis work or even some coursework is based on OpenFAST. And then, another quarter of the pie is probably designers, whether that's floating platform designers or turbine OEMs using it. And the rest of the pie is like some of the certifying bodies, some research organizations, consultants, and so on that use the tool. In terms of industry use, I would say there's kind of 5 levels of usage. Obviously, we love it when people fully base their designs on OpenFAST. That's like level 1 that we call there. They use it, they coordinate with NREL. I want to make that clear. This doesn't really apply to universities much, but like if there's still industry partners out here in the house, there's quite a few industry partners that we basically work with day in, day out. We have funds in mechanisms to basically, while the software is free, if you want our help making improvements or helping with applications or verification validation, NREL can be made available to do that. And so we do have quite a few ongoing collaborations with industry to further advance these tools. So some are at that level. Some industry members are more like, we don't necessarily need NREL because we do work ourselves, but they take it and use it internally, maybe make modifications themselves. Some users, maybe rely on some other software and they're taking sections of the code, maybe a module or maybe a aerodynamics piece of the code. Some are using it more to verify or check their own internal proprietary tools. And some just really more collaborate in terms of, we have our software, we're not really using yours, but we're working together in the sense of just verifying and validating against data sets and so on. And again, I would say contributions from external community is growing. I think that's really our goal, and we hope to see that, increase over time. That was pretty high level stuff. Any questions on that before we jump into making sure we can understand the source code a little bit? No? Is my mic on? No, it's not on. Maybe the battery died. No, please. Oh, you turned it off. Okay. Yeah, sorry about that. Better? Sorry about that. Okay, a little bit about source code. Mostly talking about, we're not going to go step through the source code, obviously, or show you all the source files. I just want to make sure we're clear on how the code, really in terms of this modular architecture, is structured. So the first thing to understand is data structures of the code. So just a couple of highlights here. I think that top figure I'd showed before, where a module internally has states and parameters, it has inputs going in and outputs coming out. Again, I represent these variables there. If you look at all the modules that are sort of at this level, so anything that's a state, anything that's an input, anything that's an output, anything that's a static parameter actually gets stored in very specifically named data structures. And you can see them there. So all inputs you can find in the code have a U percent symbol. If you search for U percent, you will find inputs in the code. Likewise, the states, and we try to tie them back to the variables here in the slide. So continuous states are X, discrete states are XD, constraints are Z. We have other states actually called other in the code. And all parameters, all the fixed things are called P. There's a few other data structures that we generally define. Haven't really talked about how the code is initialized at time 0, but there's things like module share at time 0 to say, if I define gravity in one module, another module needs gravity, we simply pass that data over. So we have some initialization inputs and outputs to make that happen. Otherwise, so everything that's sort of at this framework level where we need to exchange information, we store in data structures. And the only thing that's not in these data structures are all sort of local variables. That give an index that a subroutine needs or some local value and some calculation would be stored locally, but everything that's the framework wise is stored in these variables. There's a few things like local variables that end up being like I need to have a local variable that's a huge array, and instead of having defining things like that locally, we have what's called a miscellaneous variable in our framework that's really added for efficiency. So it basically could be a local variable, but we've put it into the framework sense so that it doesn't need to be recreated every time step like a local variable would be. So all of the things shown here in this list of data structures are actually defined in what we call a registry file. And so every module has a registry file. And if you want to see what a given module, I kind of showed the pictures of each module by module, what's its states, what's its inputs, what's its parameters. You can actually go to the registry file for that module and see the list of variables, and they'll all be there. So the inputs are clearly defined, the outputs are there, at least in terms of variable names. And then you can search those variables in the code and see exactly how they're used. When you compile OpenFAST, there's this thing called a registry. So these variables get defined in this registry.txt file. And when you actually compile, it runs through this OpenFAST registry executable, and it generates basically a Fortran F90 file to store all the data and procedures that are needed to work with this data in these types files. These types files have these four main auto-generated routines in them. And the key with these types files is you never touch them. Like, you can search them and see what they do, but you never actually physically change them because they really are auto-generated by this, what we call registry. And so again, never change a types file. You can obviously see what's inside it. But it really, all the information that you'd find in there is basically defined by the registry file that it was used to create it. So these are the four main auto-generated routines that are in those types files. One is what we call interp extract of input. And if you remember back in the first session, we talked about the first step in the algorithm is to extrapolate inputs out in the future. To do that, we basically have this auto-generated routine that does that, whatever the inputs, these are defined, or were defined in the registry, this routine will do that extrapolation for us. Similar routine exists for outputs. And then we have a couple other things. Copy and destroy is useful because a lot of the data structures are stored as complex data structures in modern Fortran. I guess it's as close as we can get to an object in a C type code. So because they're complicated things, we have routines that say, if I want to go from one value and pass that data to another, we have a copy routine that would do that. We also have a destroy routine that sort of clears all the pointers and so on. So again, these are things that we don't want to have anyone have to ever touch. They're auto-generated by the registry. The pack and unpack stuff, that's really used for the save retrieve capability or for the checkpoint files. So again, that's what's in those types files. You never need to touch them, but you can certainly look at them if you want to see what's been generated. But the registry files, of course, definitely we change every time we add, need to change any of these parameters. We add states or inputs or outputs or parameters, we change the registry file. So hopefully that makes sense. Next, about some of the core subroutines, again, module by module. This is what the sort of data flow looks like. So first of all, we were talking about, so every module basically has, I would say, four main routines. Every module of OpenFAST, so all 20 modules have four main routines. One is called the init routine. That's like the first module we call at time 0 to initialize the model. So you see how it works there. We send it any initialization input data, like if that module needs to be initialized based on someone else's output, that's what goes in there. The suggested time step, the glue code, you define the glue code, you define this DT, that also gets sent to the module to say, you can use that value or not, but that's the one we're recommending from the glue code. And you can see everything that the init routine sets. It sets its own time step, whatever that is. So normally what the init routine would do, of course, it would read in the input file of that module. It sets the parameters of that module, so all the things that never change again, it's setting them in that init routine. Again, it sets its DT. It sets all the initial states, so the X, the XD, the constraint at time 0, it's setting those. That's what the init routine is doing. It also sort of guesses what the input would be. Sometimes it doesn't know anything; it just sets that to 0. But sometimes it can get a good guess of what its input would be. We use that because some of these modules again are implicit. We use a Newton scheme, and I need something to start that scheme with. Yeah, I think that's all. The rest of that is fairly standard. There's error messages. If something goes wrong, like the file that you give it has a syntax error, like Emmanuel was talking about, it'll throw out an error message. One key thing is that the modules never abort the code themselves. They simply return an error flag and say, okay, something happened here. I can't finish my job, throw an error message, and it goes back to the glue code that called this module, and the glue code will finally abort OpenFAST. So the modules don't do that. So that's the init routine. So you need to find anything about initialization variables or parameters, you go into init. Likewise, the end routine is very similar. That's really you call it once at the end of the simulation. You basically send all the main variables of OpenFAST or for that module into it, and this really just deallocates things. It clears out memory, closes files, and so on. That's the point of the end routine. So those are the sort of beginning and end routines. And then in terms of time stepping, there's a few main routines, and these are the two main ones. Every module you see will have these two at least. Some have more, but these are the two ones you'll always see. So one is calc output. That I'll talk about the bottom one first. That's that big Y function we talked about very much at the beginning. It's just solving algebraic equations. So given the inputs, and you see the inputs going in there, given the states of that module, obviously the parameters and the current time. So given all this stuff right now, this simply returns the output, Y. So that's where that calculation, that big Y function is it within that routine. So if you want to see how the outputs of that module are calculated, go to this routine. The next one above that is the update states, and that's what's taking our module and going from time step n to n+1. So that's where it's doing the one-time step integration of that module. And you see what's going in there. We have, of course, the current time, say n. We also send the index n to it in case it needs it. We send the parameters that module to it. We send the current states. You see x, d, and z, and other states like the binary states or whatever. We send those all in. Then the other two things you see there are the inputs. We have an input, and it's not just a single value. You see it as an array, as well as the times of those arrays, and that's because that module again may need to know, values across some trajectory. So normally that array contains, the n-1, maybe the n-2 value of past history, so that when you call these interp extrap routines, this routine can basically access the inputs at any time in that horizon. So if it needs to know the n+1 value, we can call it interp extrap based on that input array, and it will be able to calculate that input at that time. Again, you can see the states coming in at t, and all the states are being updated to t plus delta t. That's really what that module is doing. So all the integration happens there. There's three more routines that you may often see. And these are really what I call, the big X is the first one. That's the continuous state derivative. So given the states and the inputs, what's X dot? That's what continuous state derivative is doing. It's basically just defining what that ODE is. Update discrete states, that big XD function we talked about earlier. Given values at t, it basically advances to t to n+1. Calculate continuous calculate constraint state residual is the routine that will return the big Z function that we want to zero out in our constraint. So again, when you're searching the code, you'll find these routines in them, and these are the ones doing the math that we talked about at the very beginning. You can find it again. All 20 modules have these routines in them, so that really should help you start focusing in on where you need to search in the code based on what you need to find. This is very, very small text here, but this is just showing that a lot of the modules, again, where we have linearization support, also have Jacobian routines. These are basically returning all the Jacobians that, of the state equations, continuous, constraint, output, with respect to the states and the inputs are all happening in these Jacobian routines. So those are the main routines you'll see, and these are basically the routines that the framework supports. Modules may have other subroutines that are more like local routines that it uses for intermediate calculations, but these are the sort of core things. You can always track it down to these main routines. So any questions on that? I don't know if people have looked at source code, but that should at least help you enough to figure out where to find things, module by module in those routines. Yeah. Use case for looking through the source code. Well, yeah. Well, obviously, if we're going to make any changes, to functionality necessary. I mean, I think a big advantage of OpenFAST convert to commercial codes is that it is available. Like you can look under the hood; it's not just a black box and figure out what's going on. Again, you can't look through the whole source code; that would take you years. But what is dynamic stall? If I select this dynamic stall model, what is it doing? You can find that, and it's probably only 100 lines of code. So and you can try to track it through these various routines. So if you have any question, I don't understand this. What is it doing? It's right there. We don't hide anything. So that's the big thing.
Error messages.
Error message. That's a big one. Yeah, very, very good point. You've seen it in some of the examples in some of your challenges. There's a specific errors point now. Like, I don't have no idea what that is. Search for the strings in that error message, and you'll find exactly where it is in code. So, again, something a commercial code can't give you. So it's valuable. Any other questions on source code, data structures? This one's called the overview on the GitHub site.
Oh, the GitHub site.
Yeah, sorry, not the GitHub, the Google Drive link I'd sent. Yeah, I actually added that section last night based on conversation. So if you didn't download it like earlier today, you probably don't have that section, but it is in there now. So, yeah. Okay. The next section is really more, I guess, for people who are used to, if you're haven't used OpenFAST, you're just new to it, this is maybe not too interesting, but it's like what we've been doing recently and some of the things that are coming up very soon. So that's what this section is. I split it into kind of 3 different areas. One is like code development. One is on verification and validation, and just brief highlights on some applications we're working on. So one thing that this was actually complete now, but Emmanuel did some great work. I think presented at TORC last year. Is that right? Was on linearization of aerodynamics. I think before we had this frozen wake option, which was fine. If you really want to know what the influence of the aerodynamic states are in a linear sense, this is really important features. So it applies both to the dynamic wake as well as the unsteady airfoil hysteresis loops. So yeah, again, internally there's some differential equation there, and we can fully linearize that now and give you the basically linear form of that, which I think is very powerful. Really useful when you're doing things like aeroelastic stability calculations, aerodynamic damping, aerodynamic stiffness. This is really important for that. That one is available. That's complete. Tail fins, I believe, is ongoing. I think the full structural thing is now released, if I know correctly. So like that hinge degree of freedom for the tail, the inertias and so the tail is there. I think the aerodynamics, we have a simple option in there now. And actually, I believe Abhineet Gupta this week, I missed the presentation, but presented on a much more improved aerodynamic model for the tail fin. Again, I'm not sure anyone in this room cares about this, but this is for small wind, when they have tails. Some cool stuff going on for the tail aerodynamics there. That's coming soon. Emmanuel, a really nice presentation on this one this week, showing our BEM improvements for 2 things. One is high skew. So if you have a high yaw air or a high tilt or something of the turbine, this is showing the comparisons of BEM old versus new relative to OLAF, where we trust it definitely more. And basically the old code, things like power were like a cubic loss, a cosine cube function. And I think in reality, it's, cosine squared or close to that. And the new BEM definitely shows that, which is great. So high yaw, much improved in this version. The other one I know Manuel's still wrapping up is high shear. I think we got mixed results so far, but that's coming very soon, at least what we've done so far. Or on offshore, this is now a few years old, but I think it's still important to mention because I think some people still may not really fully realize it's there, is that we can now do full hydroelastic flexibility of floaters. I think before OpenFAST 2.6, maybe it was, the floater always had to be a rigid body. So, rigid body motion was fine, you get the moorings, but you could never find loads in the substructure. Now, with Subdyne fully applied to floating, we can do, things like the Steesdale Tetra Spar here, which actually we've got a nice project with Steesdale. And so all those beam elements are now hydroelastic elements, and we can do that quite well. Another one that's coming, this is actually kind of coming 4.0, constrained new wave theory. If you're familiar with hydrodynamics, usually when you're running like a 50-year extreme sea state, your 50-year HS, but you also say, well, I really want to make sure that the highest 50-year wave that ever happens in this simulation. I don't want to run it 500 times to get it. I want it to happen right now. So constrained new wave theory allows you to do that. You basically have this irregular sea state. And then in that sea state, you can basically say, at this point in time, I want this wave height to hit. Usually it's, a factor of 1.86 times HS or something. But you can define it to be whatever. And this, constrained new wave theory is a cool way of looking at sort of the low probability statistics. And they all sort of, you see, this is lots of seeds of the same irregular sea state with the same constrained waves. You see it, everything sort of, no matter what the random sea state looked like, eventually it sort of builds up. We got waves kind of stacking on each other, and then boom, you got the big wave. Really useful to do, you can run hundreds and hundreds of seeds and eventually find this wave, or you can now force it to happen. So I think that's a pretty useful feature if you're trying to do, the extreme wave events. And that's actually also fully second order accurate. Another thing coming in 4.0 is wave stretching. This is like a very simple thing, but hasn't been in OpenFAST for a long time, unfortunately. So that's now fully in there in 4.0 with this new C state module. Different stretching options there. And Emmanuel mentioned this as well. I think with the new C state module, we now have a full 3D plus time grid of wave kinematics. So historically in OpenFAST, the wave loads were always calculated at the undisplaced position. So wherever the node was in the structure, it would apply the wave force there. But if it drifted off 20 meters, it would still force was assumed to be at zero, which was fine for small displacements, but for large displacements there was a phase error that you'd always see. And so now with C state module again coming in 4.0. Instead of defining waves at just the hydrodynamic nodes, you now basically define a big field, just like you do in TerpSim. Here's my big grid, and basically the floating body will move within that grid and take local values of wave kinematics. So there's basically a lot of interpolation that happens there. So obviously a little bit more expensive on the hydrodynamic setup to define waves in that whole grid, but much more accurate if you have large displacement. That applies both to the strip theory as well as to potential flow. So potential flow is another interesting thing. You can see it in the sort of top, I guess you can see it here. I plug my arrow to this one. We actually solve the potential flow solution in every point on the grid as well, and basically interpolate between potential flow solutions. So it applies to both strip theory and potential flow. And then finally, I think this is also maybe a year or two old now, but floater controls is something we've done a lot of work with. This was a lot of Andy Platt's thing here. And we mentioned some of these before, like TMDs now, you can place them anywhere, as many as you want, anywhere you want. Active cable tensioners, I think there was a question about that earlier, both in the substructure and the moorings. Don't have a picture here, but also tuned liquid column dampers, like those H tubes of fluid with some sort of constraint in the middle. You can build those, you get anywhere in the system you want now, as many as you want. So that's multi hydrodynamics. This one I presented earlier this week, if you were there on Tuesday, introducing the tight coupling option. Really useful for anytime you have beam dynon or subdynon, where that's coupled with beam dyne to elastidine, subdyne to elastidine. Right now, it all works like in the code you have, but it can be slow because the time step likely has to be smaller than you want it to be. With tight coupling, basically, you can choose whatever time step you want, likely a lot bigger than it is now. And we're looking at speeds of 10 to 100 times faster than we had before, which is great. So, yeah, great work by Derek to make that happen. And that's coming in 5.0. Like I said, the land-based version is available now if you want to just do land-based systems, but the offshore stuff is coming in the future. And then another thing, we haven't really announced this publicly yet, but we are working with an industry client to add this feature. Emmanuel talked a lot about, well, talked some about trim solutions. So if I want to find some steady state to linearize about, or maybe I want to, get some steady state before I run my simulation. Right now, you sort of have to march through that transient, have it track and find a steady state. Nice thing about it is the equations are there, and it's really just a nice algebraic system to solve to make this happen directly. And so we are working on this. I can't say exactly when it's going to come out yet, but basically allows you to bypass the whole trim calculation and just say, here's the steady state value. From this wind, this wind condition, what would it be in steady state? And then you can either do linearization there or do time domain simulation from that point. So we're excited to see this coming in the future. V&V, go through these things quickly. There was a question earlier about, what sort of V&V data sets are available. This one is the one I know is public domain. Within task 29 and 47, we have this data set from Dan Arrow in Denmark, an old, bonus 2 megawatt turbine, now Siemens, but Siemens doesn't set its turbine anymore. So a lot of that data is basically public now. Has really nice inflow and pressure sensors on the blade. It doesn't have all the fancy things of like raw, but it's a great data set, and we still use it for validation, and that thing is available. You can see a lot of the work. That's a lot of what Nano based his improvements to BEM on was from this data set. Raw, I think there was a whole nice session on Wednesday about this at the conference, but this is like our best experiment ever in terms of like, measure everything we can about the inflow from, vertical steering LiDARs, scanning LiDARs, spinner LiDARs, there's a Met Tower there, and some radars as well, both the inflow and the outflow. So we're tracking outflows. What's the wake doing, Travel D, and of course, there was a nice thing about photogrammetry and so on. So really, really nice experiment. Obviously, we're not going to guarantee all that's going to be public, but there will be benchmarks coming from that campaign coming in the future. So at least some of this data will be made available. We're constantly in the process of validating OpenFAST against that data set. And there'll be certainly, reports that come out and papers that come out with results. For offshore, a couple things that have happened recently. There was a nice wind tunnel test at Polimi in Italy that we did some great work for floating wind validation, where they've shown like a shaker table there, where the rotor was like surging and pitching in the wind tunnel. And we just said, well, how does our aerodynamics model work if the rotor moves like this? And actually, we were quite surprised it worked quite well. Likewise, we just completed a phase of OC6 with this Steesdale tetraspar in a wave tank. Also show quite good agreement. I think there's a wind energy science paper under review right now. You'll see that. You should be able to find that online if you want to see the data set. Another thing that we have, and we mentioned these controls options, we've done some work with validating like TMDs in the floater, making sure we can predict that accurately. So those are some of the things we've been doing there. And then in terms of applications on the OpenFAST side, there's 3 things to mention here. I think we've done a lot of work on different floating concepts. I wouldn't say we can model everything these days, but we can do lots of variety. So, lattice towers, different floater concept, things with hanging ballast systems, even the T-Omega wind that Lou Wang presented yesterday with, wave following and weather vaning. I think things we can model these days. So that's all exciting. Not shown at this conference, but we've shown it at previous conferences, is on sensitivity work to say, as Emmanuel said, there's thousands of inputs to define in the file, and we're trying to say which ones of these really matter to get right. when you run the code. And so we basically ran lots of sweeps of studies on the inputs and tracked what they do to the outputs and said which of the inputs really matter if the goal is to get ultimate loads right, fatigue loads right. So if you're interested in that topic, we have lots of papers on that process, you know, how we do that sensitivity work, and it's really a forward propagation uncertainty problem. It's mostly manuals, great work here, but I think I would say OpenFAST has been applied a lot to design work. Emmanuel had the great ideas, you know, together with common filters, we can take these linearized OpenFAST models and basically run them real time with actual data in the field to do things like a, you know, digital twin. So basic idea here is you know some measurements off the real asset. In this case, with the TetraSpar prototype, we knew like there was a inertial measurement unit or GPS unit in the floater, so we knew the 6-stop motion of the floater. We of course had SCADA data. I think we had an accelerometer or something. So with those few inputs, what we were trying to do with this model is say, can we basically extract out things like the tower loads, and can we do that right, even though we're not measuring the tower loads directly? And so through things like linearization of OpenFAST, and Mano has a whole toolbox actually of capability around this digital twin space, basically using this more of an operational sense to track things that happen real time. So yeah, there's a nice paper published from Energy Science on this now, showing how we validated, you know, that we can predict tower loads even though we're not measuring them directly. And extension of that is, of course, you know, can we do blade loads? Can we do substructural loads? Can we do more loads and so on? So I think it's quite exciting space. And then using that information to do, you know, operation maintenance type activities. WISE is another thing, of course. I mentioned WISE is available now. I would say it's powerful, but very difficult to use at this point. Next week, we're kicking off a phase 2 of this project with the real goal of making it practical for the community to use. And so expect to see more on this. Just at a high level, what this does is it takes OpenFAST as our basically engine, both you know, nonlinear time domain at the highest level of fidelity, linearized models at mid fidelity. Also takes Raft. I don't have that on the slide here, but Raft, as Matt Hall presented on yesterday, takes that at low fidelity. That's like a frequency domain model. So it takes all these tools, combines them with the cost and sizing tools of Wisdom, as well as controls co-design methods. It really enables, you know, lots of things. You can do controls co-design. I mean, you can optimize the structure of the controller. Same time, that's the highest thing you can do. You can do basic optimization without the controller. You know, you can do structural optimization, error optimization. You can also use this code for like just design of experiments. I would run through all these cases and let it run through with no optimization. You can do that too. Basically, it ignores that loop that goes back to the driver. Yeah, so that's again, there's nice some papers on what this thing can do and case studies, and expect a lot more happening in the space in the future. And then maybe just one update on FastFarm. I know we haven't really talked about FastFarm. I think it's a lot to learn about OpenFAST here. FastFarm is a whole other level. We are curious if people want things like workshops on FastFarm. I think normally if you've gone through the trouble of learning OpenFAST, like FastFarm, you can kind of figure it out on your own. But yeah, I mean, these are some of the things going on in FastFarm because it is very related. I think this one is now complete, curled wake. We've found it quite valuable. The previous version of FastFarm only had a access symmetric wake, so things that could do wake steering, like the wake would reflect, but it wouldn't curl itself up. This is showing LES against FastFarm there. So that we found quite a big improvement for any time you're purposely doing wake steering or tilting of wakes. One that you'll see coming soon. We'll actually present this one at Torque next year, assuming the paper gets accepted, is a new wake at a turbulence model for FastFarm. I think at high turbulence density, the model actually doesn't need this, but at low turbulence density, so like stable atmospheric boundary layers, wake at a turbulence is very important. And yeah, Emmanuel's come up with a very nice solution. It's kind of based on work that DTU had done, but really extended to the farm level. So quite exciting to see. All the code now is available. Actually, you can find the pull request on GitHub now, but we're still doing the final calibration and validation against LES. In terms of validation, this is one good example. This was actually not done at NREL. It was done at the University of Stuttgart, but basically showing some nice data sets from the FINA 1 Met tower here. So the FINA 1 tower is shown there, and he kind of looked at ranges of data, plus or minus 10 degrees through that tower, through turbine AV4 and hitting AV5, and this is showing the tower base load at Dell for the two turbines. You see the one turbine doesn't really depend on direction, but the second turbine is heavily based on the direction of the wind. And sometimes it hits the downstream turbine. You see factors there of factor of 2 on Dell for that downstream turbine. And this is showing that FastFarm really does a good job of capturing the effect of the wake on the downstream turbine. Shared moorings was mentioned. People doing floating systems. In addition to wake interactions and control interactions between turbines, you can also do mooring interactions between turbines. I think that's pretty fun and exciting to do. And then maybe one application that I have here for those doing farm level simulations. We asked the question here in this study is, if you look at the IEC standard, it says there's 2 ways to do wakes for loads. One is called the effective turbulence model, a very simple, basically algebraic model for what the turbulence is going to do to your turbine. And of course, we've introduced tools like FastFarm. And so this was just taking a study, said we took this 4x4 wind farm of 16 turbines, and we did a full wind rows, a full range of wind speeds, and we said, how do these two models compare? Standard says you can use both. Do they get the same answer or not? And I think what we kind of showed in this work is that on average, the models actually do very much agree. At the mean value, but if you run tools like FastFarm, you get much more information, like the directionality. You see it there. This is showing, I think, the turbulence intensity at the different all 4 turbines as a function of wind direction. And you can see when flow is going down, from say bottom to top, the upstream turbines are seeing basically the same thing, but downstream you're seeing higher and higher TI. And you won't get that directionality effect through the original model. So if you want to really do more optimization at the turbine level, better placement to reduce fatigue loads, you can use tools like FastFarm for that. So that's just one example of what we're doing. Any questions on that stuff? Yeah.
I have a question on what's the change?
You want to answer that? We have the guy to answer that here.
Use Q event is now 2 corrections that you include, both of them written by hours. So the first one is changing the momentum patterns. Instead of 4A1 minus A, it's people first will do something different. That includes the skew angle in it. Second correction is about redistributing the induced velocity cycle against the fact that the induced velocities are not constant, and you redistribute it, you make them periodic, something like this, and in the end. And so the first part was missing, the part that corrects the momentum balance is 4A minus A, we replace it by there's a square root of the skew angle here.
Yeah, great. And there's a paper coming out that will go through all the details on that.
The writing is good. It's hidden in the version, yeah. So wait, what? Yeah.
It's hidden now, but it will become standard later. Once the paper's out and everything's done. Any other questions on that stuff? What's coming down the pipeline, or what's recent? No. Okay, final section here, just on Outlook. I can go through this quickly. So these are the sort of directions we're pursuing. I guess continuously looking at verification and validation. We want to again really have a quantified space of like, we trust it here, and outside you want to maybe look at something higher fidelity. So we're trying to really be quantitative about that. That I would say is a very ongoing process right now, focused on raw for the turbine and awaken for the farm level. As we sort of mentioned, there's definitely physics improvements that we've been working on. BEM is one that's recent, but there's quite a few things going on, hydrodynamics and so on. So we're definitely, and these a lot driven by what we see in the V&V. We find an issue. Oh, it's, high skew, it doesn't work, or it's way off. So we go back and try to fix that. So I think, any of the work you guys are doing as well, I think whatever V&V you're doing, you find issues, like it's not giving me the answer I expect. You try to calibrate it away, or you can actually fix the physics. So we've been doing a lot of that. Mentioned the sensitivity analysis work. So I think we plan to do a lot more and more of that for different load cases, different floating concepts. So I'm really trying to understand what in these huge input parameter spaces really matter when it comes to design loads. And so we have a lot more of that planned. Yeah, a lot of these things are ongoing, obviously supporting users and communities and so on. Third from the bottom there is about, machine learning. I think there's two things we're doing or we plan to do in this space. One is, how do we take results from high fidelity models? You either use that to improve the physics of your engineering model, or you can say, I just can't figure out how to do that. I'll simply replace the physics model with a surrogate. So that's one thing we're looking into, like an unsteady arrow. That may be a nice solution. The other approach here is to say, well, OpenFAST runs great, but if I'm doing an optimization, say with Flores, that's steady state, I still want to predict at least estimate what loads are using tools like OpenFAST and FastFarm to generate surrogates that can be used in lower fidelity tools. So those are where we're looking at AI ML type approaches. Yeah, it's probably enough there. In terms of V&V, what's listed here are the areas I would say we're most concerned about. So if it's not on this list, I think we're pretty confident. Maybe that's overstatement, but these are the areas where I would say always struggle the most. Sorry, that animation is going to keep going, so it's going to distract you. But the first one there is on early airfoil data. Again, these are like lifting line models. We're not doing blade resolve simulations here. So the two questions are always, the question is always how to go from my 2D, wind tunnel test or X-foil or R-foil to something that applies on a real wind turbine. The two issues there being rotational augmentation and unsteady airfoil aerodynamics. So as you can tell by OpenFAST, we've done a lot of work on unsteady airfoil aerodynamics. I think where the question comes here is how does rotational augmentation and unsteady aero really get combined at the end of the day? I think it's an interesting question. I expect more and more work in that space. High Reynolds number, obvious when you start going these large 15, 20 megawatt turbines. I don't think we really trust our airfoil data at that time. Some of the parked idling cases where have a very, very deep stall, stall and vortex-induced vibration, I think is an area definitely needs more work. Yorgos Deskos, who's at NREL, is working on a project on that right now. Hydrodynamics, I think potential flow, it solves very well. It's always the viscous part where we have issues trying to calibrate coefficients. And often we're just doing case by case. Okay, for this system, I calibrate it. Now I know it for that case, but I change my design, I have to do it again. So we're trying to be smarter on that. There's this new OC7 project is trying to tackle that challenge. How do we do this more generally? Instead of a case, it's not very useful if you have to calibrate every time. For optimization, that's pretty useless. So trying to find general trends for validation is what we're doing here. Another one, very steep and breaking wave events. You notice nothing I've showed. Maybe steep waves is in there, but nothing for breaking. Like as soon as it curls over, I have no model for that. So that's definitely something that needs to happen, mostly for fixed bottom systems. Floater motion induced aero. I mentioned some validation there. I think it matched the wind tunnel test very well, but I also think it was quite limited in what they did in that tunnel. And so a lot more work I think needs to be done on this floater moving around and what that's doing to the aero, both for a single turbine as well as for wakes. Complex terrain is definitely an area we have concern of, mostly because we can't get the great flow predictions in complex terrain. We mentioned air-sea interaction already today, a big limitation. OpenFAST, we don't cover it all, basically. So definitely high fidelity work happening now. We'll see if that leads to anything in OpenFAST in the future. Atmospheric stability is a big one. You know, say 10 years ago, no one even talked about this topic. Now all the researchers talk about stability, you know, stable, unstable atmospheres, but the industry hasn't caught on yet. You know, they have no idea how to use stability in design process. So I definitely see work in that space. Like, how do we make this practical, including atmospheric stability in design? Tropical cyclones, big challenge there. I mean, the standard has a way of predicting hurricane loads, but I would say it's not very accurate. And so doing a lot more LES type simulations, data gathering to feed design. Fast farm, I think we're getting more and more confidence for small farms, but we're completely missing big array effects and blockage. Also cluster wakes to the next farm downstream. Nothing really for that yet. Definitely a big future work item here. Yeah, so my last slide, I think, is, yeah, hopefully this is a nice summary. I think we've talked about all this, but yeah, the tools are really useful to optimize and innovate reliable, cost-effective turbines, and future directions are shown there. I like Professor Fox. That's my favorite quote from Wally. He basically said, you know, all models are wrong, but some are useful, and we definitely agree with that at OpenFAST. Like, we know that's not perfect, but it is definitely useful. We've seen lots of papers this week. Yeah, we try to find that middle ground where we work around the weaknesses, we calibrate, we validate, then we do lots of great applications with it. So anyways, that's the end of the presentation. Happy to take any more questions on that, or what, otherwise we'll leave the rest of the time for whatever you guys want to do. Yeah.
Simulation of these massive turbines and challenges.
Yeah, great question. I would say we all have individual confidence, but we still do comparisons, say like Beamdyne against Hawk 2 or something. There are differences that I'm not sure we ever fully understand. And so I think there's something that, and maybe simply just a misunderstanding of coordinate systems or whatever it is, I'm not fully sure. So there's structurally, I think, I'm pretty sure both models are right. It's just there's something missing. Aerodynamically, I think definitely there's still some challenges. You got veer across the rotor, very different turbulence scales across the rotor. I mean, I definitely challenge them. So we definitely simulate them, but there may be limitations that we haven't fully seen because there's no data, you know, at that scale. But yeah, so yes, I'm confident, but I think there's improvement as well.
Is keeping Beamdyne for such workers usually?
Is what?
You do not consider Beamdyne, you use Elastdyne. Is that a big mistake then?
And generally, I would encourage use of Beamdyne. I think you can kind of take a first pass with Elastdyne. I mean, if there's no twist, and if the torsion effect is minimal, you may be able to get by with Elastdyne. But if the blade has a lot of curvature built in, like a pre-sweep or pre-curve or something, you know, Elastdyne just doesn't have it. So you're definitely going to miss something there. But torsion is really driving my factor. You know, anything that couples the torsion, simply got to mispredict Elastdyne. Sometimes you kind of correct for, like, the controller kind of partially corrects for it sometimes. Like, okay, really a blade twists, but in the simulation, like, the blade will pitch to kind of make up for it. So maybe there's some not quite as bad sometimes, but in general, I mean, I would say use Beamdyne, and with this new tight coupling, it's going to be lots faster with Beamdyne. So yeah.
About single precision and double precision.
Great question.
Why is that?
Yes. Well, I think Emmanuel also said, like, I always recommend single. Like, we're trying to make everything. So we didn't really talk about precision of variables in the code, but actually a lot of the variables, when you define it as a float, you can basically compile it and change that float from single to double. But not everything is defined as like a single float. There are actually a lot of things defined as double. So right now, when you compile and you say double, those things become quadruple, which seems overkill. So we've been trying to, like, say everything that really needs double precision, we'll store it as a double, and everything that can be single, we store it as this float. So usually compiling single is fine because a lot of things that really need double already have double for you. I think maybe we have to reassess with tight coupling. I don't think we've gotten to that yet.
We got rid of
We got rid of that. Thanks for clarifying. But definitely, like, we're aiming for no simulations needing double. I'm not sure it's there for the tight coupling algorithm yet, but that's for release. Hopefully, we'll work on that one. But currently, like in 3.5, it's released now. There's no reason to compile on double. Like, I don't think we'll change. I mean, it will change the answers by some epsilon amount, but it's nothing in like engineering accuracy. You need double linearization, or you just output? Because I thought all the matrices are stored in double already. Questioning that, but yeah, I trust Andy as well.
That reminds me of something very important for linearization, and I'm pretty sure I did it in the example slides. You'll see that output format has been changed to a lot of digits. You need a lot of significant digits in these bin types. Otherwise, when you do the eigenvalue, it's going to get garbage out. So something to really pay attention for. Very, very important. I'm sure it's in the slides.
Yeah, so what Emmanuel's saying, time domain, like we're just looking at out files or, a few digits of precision is usually fine if we're doing time series. But if the goal of linearization is to do things like an eigenanalysis, we found that the bigger the system is, it's 100 by 100 degrees of freedom or something. If we don't have high precision on linearization, the eigensolver basically gives you garbage. It's not like the linear model is wrong, it's just that there's not enough precision in that model. So it's like approximation of the real linear system in that sense. And so, yeah. So we always recommend delinearization, output, double precision. Yeah.
But I've been using with OpenFAST, people would do WISE.
So WISE is really the engine to do the analysis, to do the process, like the whole process. But the simulation engine in WISE is OpenFAST. So it's not like you're not using OpenFAST. It's just you're running it through the WISE driver. I can just jump quickly back here to where WISE was, because I think step through the flow chart. You see actually in this flow chart here, so OpenFAST is right. OpenFAST is here. This is where this is where you run your IAC design load cases. And there's really 3 levels of fidelity right now in WISE. You can nonlinear time domain, linearized time domain. So that's you take this model, you generate the ABCD matrix, and you basically time integrate that ABCD matrix. So this, of course, is much faster than this because it's all linear now. And then frequency domain, that's the raft code. And so when you're doing this, you're not really interacting with OpenFAST. Like all that's in the background. You're really interacting here at the WISE level. And so you do basically, let's see where the input files are here, but you have this big input file that's WISE formatted, and it's YAML files, and it has like all the information OpenFAST needs to do with simulation, plus everything needed to run the analysis. So this is where you basically set up your load case. So here's the load cases I want to run. The sweep of wind speeds, wave conditions, whatever it is. You define that in the WISE input file. WISE will then basically go, and pre-processing is basically setting up all the steps we talked about to generate all the input files needed for OpenFAST. If you're changing blade design, it's regenerating the mode shapes for you, say if you're using elastidine. It's all built into that. It's running all the, this is all the terpsim. It's generating all the terpsim files for you if you haven't generated them already. Then it sets, creates all the OpenFAST input files for you, runs those simulations for you, and then does all the post-processing. So, stream event tables or dimensional loads, it does all that. And then, yeah, again, you can do more design experiments where it's like, that's just running load cases and get the answer out. If you want the optimization, you basically, what you're optimizing for, and you can build that in there as well. So that's where we're trying to go. Again, this will be our load case script, but also our optimization script. Yeah.
Can do so many things. Why is it called just so?
Why is it what?
Why is it called just so? Something related.
Yeah. That was a sales pitch, but to be honest, I mean, we were trying to like sell this to RPE is like, this is, controls code design, and it can do that, right? Because it can do the structural optimization, the error optimization, the control optimization together, which is quite different than, traditional industry where you may design structure or throw it to controls engineer to do the things. We're really trying to do, because there's a lot of controls code design methods built into WISE, but it can also do the simpler sequence type of optimization as well. So yeah, I mean, that was the name we gave it just because it was WISE. That sounds smart, right? But yeah, I mean, it's a name. So yeah. Andy just perked up. I always ask Andy that question because he's in charge. That's what I was. That's great. That's exactly the answer I was going to give, and I'm very happy Andy confirmed it. So usually I say something, and then Andy says, no. You're forgetting something. I would say with 4.0, if you actually go to dev now, like all that C-state stuff is in there. That's all been well tested. I think we're waiting on a few things for 4.0 to make complete, but all that hydrodynamic stuff, we've actually been using it for the last year at NREL. So, I mean, it's basically ready to go. It's just been in the queue for everything else. So, yeah, if you want to use C-state now, use dev and you'll get it. Don't wait till December. Yeah, anything else? If not, I'll probably just close out the recording for next, and then yeah, we still have, I mean, there's still time. So if people want to do more simulations or have questions on what they've been trying to run, we use the time for that, and yeah, it's up to you. So thanks a lot for coming. I know it's been a long day and a long conference, but thanks for staying with it, and hopefully you guys are going to be powerful OpenFAST users going forward. So thank you.